reservations in two-way slabs by means of yield lines. In this video, we will handle the case 7, which is a type of hole in a configuration of a slab where the three sides are simply supported and one side is fixed. The orange indicates simply supported, the dark green indicates fixed or a continuous slab. So we will handle case 7 with a corner square hole. Let's consider now a rectangular slab with sides A and B fixed on the top. Then we'll draw the yield lines. It means that in a corner where one side is fixed and the other simply supported, then this is 60 degrees and this is 30 degrees. We use this simple 30, 45, 60 degree rule as an approximation, but this will do for the moment. The other corner exactly the same. Then we have the yield line at 45 degrees. And then we make the connection between those yield lines. Of course, where the slab is fixed, there's also a yield line. Then we make a reservation in the top left corner of the slab, where the yield line disappears, of course, because it's cut. The reservation has a dimension d1 times d2. Because we are handling it for a two-way slab, means that the length b must be smaller than 2 times a. Case 7, to describe the conditions of case 7, means that the corner yield line, the tip or the corner of the reservation must be on the yield line. That means that d2 is equal to d1 times s1 divided by s4. S1 is this, and S4, of course, is that. Then the top left corner means that D3 and D4 are 0, and the cutting only one yield line means that this reservation will not pass this point, or that D1 is smaller than D4. Why do we make all those conditions? Because we cannot find a solution in one closed formula for a random reservation in the slab. Now, the case 7 slab, or the case 7 hole or reservation in the slab, when we look at those conditions and we run through it, then you will see it will be a reservation on the top left corner. It will grow bigger and bigger until you reach the end. So that gives you a picture, a visual picture of how those reservations can look like. We can also put in some numbers from the previous slides. We know what S1 and S4 is. It's just geometrics. And okay. Now we will try to calculate the maximum bending moment. We can divide the whole slab into a summation of triangles and a summation of rectangles. So when we look at the work done by the external forces, and we look at the rectangular portion, then we see that the dimension is A times B minus 2 times S1, which is this one and this one, times the mean deflection, which is delta divided by 2. So that's where the 2 comes from. Plus the summation for the triangles. We have on the left-hand side A times S1. On the left-hand side, also A times S1, but we will subtract the reservation in it. So it's 2 times A S1 minus the reservation, which is D2 times D1. And the total deflection is then D1 divided by square root of S1. Square root of S1 is equal to S4. It's this side. This side. Then we can substitute the different values and we get an expression for E EX or E over Q delta. Then we look at the work done by the internal forces. Then we will take the yield lines and project it on their axis. So then we got this yield line projected to the rotation axis in the north. And we see that the total length is then, when it's projected, is B minus D2. And the angle of rotation is delta divided by the maximum distance S4. Then we have also this rotation axis and the yield line. It's B minus D2 divided by S4. Then we will look at the bottom side. This is B projected on this rotation axis, so it's B divided by S1. On the right-hand side, it's A times of A divided by S1. And on the left-hand side, the total length of this yield line projected to the rotation axis is, of course, A minus D1, and the rotation angle is delta divided by S1. We put in the numbers for S1 and S4, and we have this expression for the work done by the internal forces. When E is equal to D, we can find M, and M is then equal to this expression, this formula. We have taken the plastic bending moment on top of the slab equal than the one on the bottom of the slab. It means that the reinforcement on top is equal to the reinforcement at the bottom of the slab. If not so, then we must adapt the M accent or M1 of the top reinforcement. Let's just give now an example. We have a slab of 5 by 6 meters with a hole in it or reservation in it of 1.33 by 2.3 meters. The depth of the slab is 15 centimeters, the concrete cover 30 millimeters, the floor finish, some tiles, is 2 kilonewton per square meter, and the mobile load is 10 kilonewton per square meter. And we want to know what is the needed reinforcement for this type of slab. We start to calculate the load in ultimate limit state. We got the permanent loads, which is the proper weight, 0.15 times 25, plus the floor finish 2, this all times 1.35, and 1.5 times the mobile load. It gives you 22.76 kilonewton per square meter as total load on the slab. B dimensions, A was 5, B was 6, D1 2.3. And we use the formula from the previous slides, and we see that the maximum bending load when we put in the different numbers, is 24.46 kilonewton meter per meter. The lever arm in the X direction is then the total height of the slab minus concrete cover minus the point of gravity of the reinforcement. We suppose it's only in the direction X, one layer of reinforcement, and we use a diameter 10. And we have 150 millimeters as lever arm in the X direction. In the Y direction, which is the second layer, it will be 105 millimeters. And we calculate the needed reinforcement by using the mean lever arm, which gives us 110 millimeters. The needed reinforcement is then equal to the bending moment divided by the lever arm and augmented by 10% because this is an upper bound method. We have then 1.1 times 24.46, then for the units times 10 to the power 6, divided by 0.9 times the lever arm times the yield strength of the reinforcement. And it gives us 625 square millimeters per meter, or a diameter 10, 8 diameters 10 per meter will be okay. So the slab is okay when there is a reinforcement of 8 diameters 10 in X, Y, direction, top and bottom. Let's now look at a second example. Now this time it's an existing lab reinforced in two directions, top and bottom also. And then we ask ourselves, is it okay to make a reservation in the corner by 2.5 times 1.4 millimeter? We do not know the original load that was used to calculate the existing reinforcement. So that's why we will calculate the bending moment of the slab without the reservation, but we don't know Q, so we divide M0 by Q, and what is left is only dependent on the geometrical characterizations of the slab. So M0 over Q gives us 0.833 millimeter per meter. And the maximum bending moment with the slab, so we take M divided by Q, we take the formula of the previous slide. This is only dependent on the geometry, and we get 0.937 millimeters per meter. So this means that the bearing capacity is 89%, or we will lose 11% in bearing capacity. So making this type of hole in this type of K7 hole into the slab will lead to 11% less bearing capacity than previously. So let's talk a little bit about the bearing capacity. It's defined by 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. The bearing capacity is a function of A, B, and D1. D1 is the size of the reservation. D2 is automatically coupled to D1 because the type 7 reservation requires this. Then we will try to work in dimensionless units, which means that D1 equals alpha 1 times A and B equals alpha A. This type 7 corner hole will then, we can rewrite the restrictions by saying that for a two-way slab, alpha must be between 1 and 2. And for the type 7 hole, the alpha 1 must be between 0 and 0.634. And then we can rewrite the bearing capacity of the slab in dimensionless units. Let's put this in a graph. On the bottom side, it is alpha 1, which is the size of the reservation with a maximum of 0.664. And on the y-axis is the bearing capacity. And we draw the bearing capacity in function of the dimension of the hole, but we draw the red line in function of square slab because alpha is 1. A slab with alpha 1.5 and a slab with alpha equals to 2. The first thing we notice is that by making a K7 corner hole in a rectangular slab, it will always influence the bearing capacity of the slab. It will always be lowering the bearing capacity of the slab. So in the top corner, it's not a very good idea to make a reservation on that location. Then let's look at some visualizations. When alpha is 1.5, then this side or this side here is 2 times this side. And alpha 1 is 0.637. That means from there to there it's 0.637. It's a reservation like that. So this yield line will disappear. If you make a hole like that, the bearing capacity will be only 91% of the original bearing capacity. Or when we look at a reservation with size 0.423 times the size A, then the bearing capacity is 10% less. Or when we make a small hole like that, then the bearing capacity is 94%. Looking at those, let's put it this way: the alpha is always between 1 and 2. So this curve is an extreme, and this curve is also an extreme, and all the other curves are in between those two. Each curve or each proportion B divided by A, for each of them, there is a maximum or a minimum. That's how you see it. There is an extreme value where the bearing capacity is the least. So for each B over A, there is a bearing capacity which is the least. So, and this is size of a reservation equals to 0.525 times A and gives you a minimum of 10% loss in bearing capacity. So we can now go to the when alpha is 1.5, then you have also a minimum which is 10% less than the original bearing capacity. And for a slab where one side is twice the shortest side, then there is also a maximum loss for a certain size of reservation, and the loss is then something like 12%. So this is an interesting exercise. Making a reservation in the top left corner leads always to loss of capacity. So to summarize it, these are the two extremes. A hole type 7, it means that this tip is following the yield line of a rectangular concrete slab, leads to a loss of bearing capacity of maximum 12%.